Good afternoon everyone, I am Mr. Ish. Thank you for joining me for this video. I've recently presented a video on this trapezoid area derivation using integral calculus. In that video, the way the trapezoid figure was drawn and derived, the area was 2 base times height, which was legitimate area for the area of that trapezoid figure that we were looking at, and then I showed how we can reconcile it with this. In this video, I want to show you how we can actually get to this without having to do that extra reconciliation procedure. To actually derive this still requires an assumption to be made, but it's a simple assumption and it's not too out of this world. The assumption is this: if supposedly you start with an x and y axis, you have this base, one of the bases here on the top, we'll call it B1, and you have another one right here, we'll call it B2. You know this is my y-axis and that's my x-axis, and you know you can connect it. The assumption is this: if supposedly this length of each of these segments, if this is B2, the length of the segment from here to here must be B2. Likewise, if this segment is B1, its length is B1. If you were to start plotting your points, if this represents from right here to here length of B2, then in terms of your coordinate points, this must become B2 over 2 comma 0, because then each of these segments is being split into half by the y-axis, and likewise this over here must become B2 over 2 comma 0. We have the origin down over here. Here on the top we have 0 comma h, because we know we have a height component, but this point right here must become minus B1 over 2 comma h. Why? Because if this right here represents the length of the B1 segment, at each of the endpoints we're looking at only half of that, right? This right here represents half of B1, half of B1, half of B2, and half of B2. And then this right here would be B1 over 2 comma h. Now the only problem with using all of this, which is nothing wrong with doing it that way, is you have a lot of letters over here, which naturally is the case. We got B1s, B2s, h, then we have these over 2s. So you can make a simple assumption for the derivation of this, utilizing this schematic over here, is for right now multiply everything by 2 to get rid of these fractions. See, if you multiply everything here by 2, I'm talking about the horizontal aspects, the x-axis values. If you multiply everything here by 2, this minus B2 over 2 becomes a minus B2. This B2 over 2 becomes a B2 naturally, because you're multiplying everything here by 2. B1 over 2 becomes just a B1, and minus B1 over 2 becomes just a minus B1. So essentially you're looking at something which is twice as long, but that's fine. Now if you use these coordinate pairs for your derivation procedures, then at the end you can divide that formula which you will derive by a 2, and you'll easily arrive at that. So what we have to do is remember this. Right now we multiply everything by 2, but at the end the derivation must be divided by 2 to get to the finality. All we have to do now is to decide whether we're going to do integration with respect to ax, and you know you can be looking at something with dx, or should we do everything here with respect to ay, and then in that case we look at dy. The easiest manner for this derivation using these letters you have before you, the coordinate pairs, is to do with regards to dy. And you know when you're looking with regards to dy, you're thinking about right boundary curves and left boundary curves, and you're looking at the difference. Well, if you're going to do with regards to dy, we already have our right boundary curve. With regards to the same technique, we have our left boundary curve. You know an interval must be presented here in a y-axis dimension. We have a 0, 0 up to an h. So we already have our interval set. So what will our equation be over here with regards to this schematic? The area with regards to y will be from 0 up to h. We're going to do xr minus xl dy, right boundary curve minus left boundary curve. Here the equation has to be presented in the x equals format, because we have the capital X's here. So we just have to determine the equation of this line and the equation of this line. That's it, and then we'll run it through this. At the end, of course, we have to do this divide by 2, and we'll get to our derivation formula for the area of this trapezoid. So let's start with the determination of this equation of this line right over here, xl, the left boundary curve. We have these coordinate pairs. We have minus b2 comma 0, and we have minus b1 comma h. You know you have to do change in y divided by change in x to get the slope. You have h divided by minus b1 minus b2, and you can say minus b1 plus b2, or you can say b2 minus b1. That's my slope. Y is equal to h over b2 minus b1 x plus your y-intercept, which I'm just symbolizing at this because we already have b's used up here in terms of letters. We'll just use a circle with a b for your y-intercept. We'll plug in this coordinate pair, x value, y value right here in this equation. 0 is equal to h times minus b2, which is my x value, divided by b2 minus b1 is equal to your y-intercept. Your y-intercept here is equal to all of this on the other side, which is just a b2h divided by b2 minus b1. So now I see that my equation for this left boundary curve is y is equal to h over b2 minus b1x plus b2h divided by b2 minus b1. And you have to be cognizant of the fact that we have a lot of letters over here and their handwriting must be good, so we don't confuse b's for h's and vice versa. But we have to present the equation here in the x equals format, so we have to solve for this equation in terms of x. X over here will be equal to what? This is my left boundary curve equation. It will be equal to, and we'll do it right over here, it will be y minus b2h divided by b2 minus b1 multiplied by this coefficient of x flipped around, b2 minus b1 divided by h. So now we have to determine next the right boundary curve equation. The right boundary curve is made from these two coordinate pairs, b1 comma h and b2 comma 0. Just do a change in y divided by change in x, you'll get 0 minus h divided by b2 minus b1, which is minus h over b2 minus b1 is your slope. Y is equal to minus h divided by b2 minus b1 x plus your y-intercept. We'll plug the b2 comma 0 right over here. 0 is equal to minus h b2 divided by b2 minus b1, which now we have to solve for this y-intercept. Y-intercept is equal to h b2 divided by b2 minus b1. So now suddenly our equation, the right boundary curve equation in terms of y is minus hx divided by b2 minus b1 plus hb2 divided by b2 minus b1. We still have to solve this in terms of x because we're doing derivation here with regards to dy. You can see how with regards to the previous video I presented on the trapezoid, how this is a little bit more involved simply because we have more of these difficult coordinate pairs to deal with. Now this right boundary curve, when you solve it out, becomes what? You take everything on the other side and you solve for this little x. You'll have y minus h b2 divided by b2 minus b1 multiplied by this coefficient of x flipped around. You will have b2 minus b1 divided by minus h. And that's it. That's everything laid out here in terms of our framework. We have our left boundary curve, right boundary curve. We know our interval is 0 to h. Now all we have to do is a derivation. Okay, now we have our right and left boundary curve equations set. We just have to do the actual integration. It'll be a little cumbersome simply because of the nature of the expressions that are involved, but it's not hard because it is still all polynomial integration. Let's start over here. Area with respect to y, we know already it's from a lower limit of 0 up to an upper limit of h. We have to do right boundary curve minus left boundary curve, and let's start doing it. We have a b2 minus b1 divided by minus h times that y minus hb2 divided by b2 minus b1 minus now the left boundary curve. This part right here, we have b2 minus b1 divided by h times y minus b2h divided by b2 minus b1. Of course, we have to be careful here not to misread our own handwriting so we don't end up making a mistake and it carries through. Here we basically just have to open up these parentheses, this with that, and be aware of the effect of the minus. So let's do it. From 0 to h, here I'm going to have a minus, see all of this will become a minus y times b2 minus b1 over h plus this minus, and this minus will become a plus. We'll have a hb2 times b2 minus b1 divided by hb2 minus b1. Let's look at this part right here. We'll have a minus y over h b2 minus b1. This minus and that minus will become a plus. We'll have over here b2 minus b1 divided by h times b2h divided by b2 minus b1. As you can see, it's a little messy and it's a little cumbersome, but we'll get a good answer here and it'll be all worth it. Now we have to just do a simplification. You see this b2 minus b1, it can cancel out with this, You see this h and the h's can cancel out very well. Here I have a h which can cancel out with that. I have a b2 minus b1 which can cancel out with that. So we're good. Let's rewrite everything now what we have remaining. We have here a minus y b2 minus b1 over h plus b2 minus y over h b2 minus b1 plus b2 dy. Now all we have to do is the integration in this step and we'll do it. Remember, everything here is being integrated with respect to dy, therefore we'll start adding y's for our integration. When you do the integration, the integral sign disappears. This will become a minus y squared over 2h times b2 minus b1. This becomes a b2y. This here becomes minus y squared over 2h b2 minus b1, and this b2y, all from upper limit of h to 0. The zeros are meaningless here, so you only have to plug in the h's, and we'll do that. Let's plug in the h's in the places of y's. We'll have a minus h squared over 2h b2 minus b1, and we'll simplify in the next step right in these existing lines, plus b2h minus h squared over 2h b2 minus b1 plus b2h. Here this h cancels out with this square on the top. Here this h cancels out with this square on the top. So what do we have left? Now we have to actually open up these parentheses, and we'll do so. But we'll do so right over here as we open these up. When I open this up, I'll have a minus hb2 over 2 plus hb1 over 2. Minus hb2 over 2 plus hb1 over 2 plus b2h. Here we'll have exactly the same thing open up. Minus h over 2 b2 plus h over 2 b1. Remember, we're still going towards the derivation of the trapezoid formula. Minus hb2 over 2 plus hb1 over 2 plus that. Now let's start accumulating the items. Remember, at the very end we have to do everything divided by 2 to compensate for that times 2 we did at the very beginning. Let's combine the like terms. We have minus hb2 over 2 and minus hb2 over 2. These are equal to a full whole hb2 minus hb2. So we can cancel out these minus hb2s over 2s, two of those, which are equal to a single minus hb2. We have hb1 over 2 and hb1 over 2, which is equivalent to a single hb1. We can eliminate this. Now let's see what remains here. You see everything in front of you. We have a minus hb2 plus hb1 plus, we can write this as hb2, why not? b2h, hb2, it's all the same, plus b2h, we can write that as hb2, just so everything looks very uniform in terms of our reading it. This minus hb2 can cancel out with this hb2. We're essentially left with the hb1 and an hb2, and let's unify them together. hb1 and hb2. hb1 plus hb2, you can isolate an h. We have an h times a b1 plus b2. This is coming out to be the area derivation with regards to y, but as I said, we have to do everything divided by 2, and we do everything divided by 2, and there it is. So 1 over 2 times height times base 1 plus base 2 represents the area of a trapezoid, a shape which has appearance such as this with a b1 and a b2 and a height. And that right there represents the area of this in terms of the derivation that we have seen. But you can see it's a little bit more cumbersome, or perhaps much more cumbersome than the previous one. And you can see here, based on the beginning of this video, how it was plotted against the x and y plane. Everything was plotted right through the middle, so we split the b1s and the b2s into equal right and left sides. But then I multiplied everything by 2 to get rid of those fractions, and now I'm dividing everything by 2 to compensate for multiplying everything by 2 earlier on. That's all I wanted to present in this video. I hope you enjoyed it and it was not too confusing or messy. But thank you for watching. Have a nice day.